All right, so this is very similar to the problem we just looked at, but now we're looking at a given point. So the slope of the tangent line is and always will be the slope of the tan equal to the limit as h approaches 0 of the slope of the secant, which is f of our point, which in this case, this is like a, f of a. So a is 1, so it'd be like 1 plus h minus f of 1 all over h. Correct, because you can find the y if you have the function. And then that is equal to the limit as h approaches 0 of 1 plus h squared minus 3 times 1 plus h minus negative 2. Because again, f of 1 is negative 2. They already plugged it in and did the hard part for me. All over h equal to the limit as h approaches 0 of 1 plus, if you FOIL 1 plus h, you get 1. Then you get 1 times h and 1 times h, so we'd get 2h plus h squared minus 3 minus 3h. A minus gave a positive 2 all over h. One, negative 3, and positive 2 are all like terms. So 1 plus 2 is 3. 3 minus 3 is 0. So 1, negative 3, and 2 all cancel. Hopefully at this point you notice you have an h in each term. So we can also cancel an h from the bottom. Leaving me with the limit as h approaches 0 of 2 plus h minus 3. 2 and negative 3 are like terms, so you get negative 1 plus 0 for h, or negative 1. So the slope of the tangent line to the graph at that point is negative 1. Are we feeling better? Okay, so today is the second part of rates of change in tangent lines. We're still looking at average rates of change. So again, the average rate of change is the slope of the secant. That's f of a plus h minus f of a all over h. Or old school y2 minus y1 over x2 minus x1. And then the tangent is the limit of that. And the normal line is what we're going to introduce today. Yes. They're actually identical. So in this case, y2 is really like, in this case, the change from y1. So all h really represents is the change from like x1 or y1. So if you had a graph and this was my a, then here's my f of a. If you think about that like my x1 and my y1, the next point on that graph is like your x2, y2. When we do the a plus h, all we're doing is saying the distance from here to there is a plus h, because h is the distance between them. Pretty much. Exactly. Exactly. So I like to always give equivalent statements. These are all statements that mean the same thing. The slope of the function at x equals a is an equivalent statement to asking you to find the slope of the tangent line. So the slope of the tangent line is the slope of the function at x equals a. The instantaneous rate of change is also the slope of the tangent line. And the limit as h approaches 0 of f of a plus h minus f of a all over h is the slope of the tangent line. So these are all equivalent. Yeah, it is crappy. Yeah. You only have a week off. You only have a week off for Christmas. That's usually when we do our TFIM volleyball. Wow, thanks. All right. Yeah. We're not allowed. It's contact, so they don't want like male students against female teachers, or like this is another example of like ones that were really kind of getting you on the homework, and so the more we do the fractions, the easier they become. So if it asks you to find the slope at x equals a, then it would be the limit as h approaches 0 of 1 over, remember it's a plus h minus 1 over a all over h. You need the common denominator. So we multiply the first fraction by a. So you get a over a plus h. The second fraction by a plus h. So we get a over a plus h all over h. And again, we don't want a fraction and a fraction, so we'll multiply by 1 over h. So you get the limit as h approaches 0 of a minus h all over a h a plus h. a minus a is 0. H over h becomes negative 1. I get negative 1 over a plus h. Plug in 0 for h. I get negative 1 over a squared. You never, ever want to mathematically alter the denominator. So always keep your denominator undistributed. The numerator, distribute, go to town. Denominator, don't. Because typically things from the numerator just cancel with an undistributed or unsimplified denominator. Yeah. Because I didn't distribute. Like if you had a plus h, and I told you to multiply that by h, like ignoring everything else in the problem, even if I had distributed my a, like originally, and then you had the h, it would become a squared h plus a h squared. If I told you to work backwards and take out the GCF, and I just need space, your GCF would be a h, leaving you with a plus h. So it's essentially just not distributing the GCF. Multiplication is commutative. So where that h is doesn't matter. I literally just rearranged the terms and brought it to the front. So does that kind of answer why it doesn't do anything with the a plus h? Yeah, it would be like, even if those were numbers, right? Like say a equals 2 and h equals 5. If you had 2 times 2 plus 5 times 5, if you distributed it in here, it wouldn't stay out there, I guess is what I'm getting at. Like you have to pick where you distribute the h. Okay, so that's part A. Part B says, where does the slope equal negative 1/4? So remember, this right here, this equation, negative 1 over a squared, represents the slope in general. So if I want to know where that slope is equal to negative 1/4, I have to set the general equal to negative 1/4. So in this case, that would be when a is 2. Yes. No, it can be negative 2. It's going to be both. It's going to be 2 and negative 2. So if I was running out of room, I'm just going to erase. Because if you cross multiply, you get negative a squared equals negative 4. So a squared equals 4. And when you square root it, anytime you take a square root, it is plus or minus. So algebraically, that's why it could be both. I was going to show you graphically, but Corey hit me before I needed to. No, you're good. I like it. Because I was going to talk about the fact that if you think of this function 1 over x, it's symmetric about our origin. So if a point exists on the positive, then it has a point opposite on the negative. Okay, let's talk about the last part. It won't erase. Oh, my pen died. What? The Apple pens? Yeah. Well, this is an off-brand Apple pen, but yes. Yeah, this one was like 13. And since I had to pay for it, that's what I got. Yeah, it's like limited to like a certain amount for teachers. I had another Apple pen. Here we go. This one just doesn't write as nicely. This one you don't have to charge. All right. What happens to the tangent if you had a point A and 1 over A for all different values? So A, 1 over A would be the tangent in general. So what we want to talk about is the slopes of the curves and the graph. So if the slope of the tangent is always negative, right? So the slope of the tangent is equal to negative 1 over A squared. If the slope is always negative, what would that tell you about the original graph? How would you get, or why would you have a negative slope on an original function? You know, I was kind of thinking more like, is the graph going to be like increasing or decreasing? Right, it would always be decreasing, right? So if the slope is always negative, the original is always decreasing. What could we say about the limit as x goes to infinity for 1 over x then? What would happen as x is going to infinity? What are we approaching? Yeah. And how about x going to negative infinity? Yeah, because there's a horizontal. What about the limit as x goes to 0? It is an infinity. Think about it. If this is the tangent and the slope is always negative, as x goes to 0, it is always going to go to, yeah, it's always going to go to negative infinity. Because this is always negative, so it's always decreasing. Actually. And decreasing, this would be positive. Yeah, it's positive on this side. Okay. Just going back to limits. Hey, not funny. A normal line is going to be your favorite thing because it is literally the opposite reciprocal of the tangent slope. So in the past example, if the slope of the tangent was equal to negative 1 over a squared, the slope of the norm would be positive 1 and a squared. because it's the opposite reciprocal. So the normal line to a curve at a point is the line perpendicular to the tangent at that point. So perpendicular lines are each other's opposite reciprocals. So if the tangent was -1 over a squared, the normal is a squared. If you use the numbers, if the tan was -1/4, then the norm would be 4. And that should make sense from thinking about parallel and perpendicular lines from all our years of study. What? A bowling? Oh, no, I don't know anything about that. Write an equation for the tangent line and the normal line to the curve 4 minus x squared at x equals 1. So we're going to start with the tangent slope at x equals 1. So 4 minus 1 squared is 3. So it would just become -3. So 3 minus 3 cancel. H squared h and h cancel. So we get a slope of -2. So the slope of the tangent is -2. The equation of the tangent line would be y minus y1, which is f of 1, which was 3, -2, x minus x1. So again, this is like my x1. My y1 is plugging x1 in. So that's how you get your tangent line equation. And then the normal line, so the slope of the norm would be its opposite reciprocal. So the equation of the normal line is everything the same except for the slope. Correct. Yep. Anytime you get asked for the equation of a tangent or a normal line, you plug your point and your slope into point slope. I told you, like, this lesson is sort of like the culminating, like, idea of everything in chapter 1. So going back to culminating all of those ideas, oops, in lesson 1, because, new book, the average velocity is the secant line now. The instantaneous velocity is what we refer to as the tangent line. So in that first section, we thought of these as slope and the limit of slope. And that's how we introduced the idea of the limit. Because we talked about the falling object and the rock, and we wanted to talk about what was happening with it. And then we looked at points as we got infinitely close to it from a table. So you started, at 1, 2, and then you got to 1, 1.5, and then 1, 1.1, and then 1, 1.001, and we found our limit. So now that same idea can be said, but what we're going to do is find that same rock falling from a height, and we're going to find it in general. So the average speed of the rock in general would be f of 1 plus h minus f of 1 all over 1 plus h minus 1. Because again, this is my x1 and my x2 because that's the interval. And my f of x is 16t squared. And this represents the average speed, which is also a fancy way of saying the slope of the secant. So plug 1 plus h in, so you get 16 1 plus h squared minus 16 times 1 squared all over, well, 1 plus h minus 1 is really just h. No, I'm just showing exactly where everything comes from. So you get 16, 1 plus 2h plus h squared minus 16 all over h. So your 16s cancel, your h cancels, and we get 32 plus 16h. So that represents the average speed from a distance of 1 plus h. That is the average speed at 1 to 1 plus h. So if you wanted to know the average speed after 3 seconds, then the change would be 3, and that would be 32 plus 16 times 3. If you wanted to know the average speed after 10 seconds, then your h would be 10, because h is representing the change in time from 1 second. This is only from 1 second. So if you wanted to know the speed of the falling rock at 1 second, then it's all of this with the addition of what? For instant speed, you plug in, you just add in a limit, right? So it wouldn't go into the 32, it just go into the 16h part. Exactly. Because again, if you think about the idea, the slope of the tangent, or the instant speed, is the limit of the secant. So we already found the secant, or the average speed. So what we're going to do is take the limit of the average to get the instant. Yeah, so you mean like if part B didn't say that's falling rock at 1, it said at 10? Unfortunately, if it said at 10 seconds, then you couldn't use the example from part A because that was from 1 to a change. So you would have to, you could still use all this, but everywhere you had a 1, you would have to plug in a 10. For the limit, yes. Correct. What would change is if you wanted, like I said, you wanted to find it at 10. Now you would do the limit as h approaches 0, but you'd have to do f of 10 plus h. I mean, I intentionally did that, but yes. You would have to put 10s back here too. Because it would be 10 squared. So this, you'd need a 10 squared here. All right, so I like all of this thought. What could I have done over here in part A that would have let me find it at any t value? What could I have changed in part A that would let me find it at any t value? Exactly. So if you wanted to find the average speed in general, to let you always find your instant, instead of using 1, you would have found the slope of the secant at f of a plus h minus f of a all over h. And then you can go plug in any a value you want. So we could have plugged in a equals 1 and found the slope, the average speed for 1. You could have plugged in 10. Like, you can plug in anything if you use the a at the beginning. Do you want to know what it is? I knew it. Yep.
Now here's my question. H is still always 0?
If you do instantaneous, yeah.
So I'd say even if we're looking for it at like say 9 or 10,
Are you talking average or instantaneous? That's yes. Then yes. Instantaneous, it's always 0. Okay, so like here, we did the average speed at 1 to some unknown distance h away. So what you could do is say average speed from 1 to 3. You would plug 2 in for h. Because remember, the equation is a plus h. So in this case, a is 1. So it's 1 plus 2 to equal 3. So the h value you plug in is 2, not 3.
So would H be the difference?
Exactly. Yeah.
So then it would be
Yeah. Yep, it'd be 32 plus 16 times 2, which is 64. So the average speed from 1 to 3 seconds is 64. Not if you're doing average, correct. Yeah, if they give you actual numbers, it's way easier to plug in actual numbers than to get it in general. Yes, yes.
Well, I guess it'd be beneficial if we had
Like number 7 on the homework. Yeah. But if you think about like 7 on the homework, what I did, and you could kind of see it as I started to write it, like I did PQ1, PQ2, PQ3, PQ4, and I wrote the 650 minus 10 minus every time. Because the first part of the equation was never changing. So like, it, you know what I mean? Yes, it is a benefit. You just have to be cautiously aware. Do the next page in that worksheet.
So if it did change, that's where it would be beneficial.
So you're doing like 1 to 7. Isn't there a paper in your pocket? Like, isn't there something after your notes? Oh, did I not staple? I stapled all my notes together. So you're doing 1 to 7 on the 1.4 worksheet. And see what I wanted you, so I wanted you to do the 1 to 7 on there, but we talked so much. I was going to have you do the part B to D in your textbook too. That's why I told you to leave all that empty space.